Bogren. SIPN was launched in late 2013. It is a collaborative network of scientists and stakeholders seeking to advance research on Arctic ice prediction and communication of sea ice knowledge and tools, with funding from NSF Arctic Science Section, the Office of Naval Research, NOAA, NASA, and the Department of Energy. Today's webinar will present a post-season discussion of the 2014 Sea Ice Outlook. ARCIS is a nonprofit membership organization with the mission to provide a catalyst for interdisciplinary thinking, leading to development of highly collaborative partnerships such as the Sea Ice Prediction Network. For more information about ARCIS activities, please visit our website. Before the webinar begins, I want to quickly review how it will work. First, as we've been saying, please mute your phone or your computer mic. We will have a series of slides from our presentation team. You should be seeing slides on your screen now. If you are having trouble connecting to the webinar, please contact Judy Fonstock at ARCIS. Her email is judy@arcis.org. We will not take questions or comments during the presentations. Both will be addressed after them. At that time, you can ask questions or add comments in two different ways, either by raising your hand in the participant panel or by typing a message in the chat panel. To open both the participant and chat panels, please hover your mouse over the green tab centered at the top of your screen above the slide that you see. That tab should say Viewing Ed BW's Desktop. From the drop-down menu, please click on Participant and on Chat to open those panels. To raise your hand in the participant panel, click on the hand symbol that is located at the bottom left corner of that panel. When I call on you, please unmute your mic or phone and speak. When you're finished, please remute the mic or phone and re-click the same hand symbols below your hand. To use the chat panel, please type your question or comment in the open field. I will read your question or comment when I call on you. Please unmute your phone and mic at that time. And again, remember to unmute your phone or computer to speak and to mute it again when you are finished. This event will be archived and available online soon after the event. Registered participants will receive an email when that archive is available. Today's webinar will include presentations from the SIPN leadership team members, including Julian Struve at NSIDC, Cecilia Bitz at University of Washington, Walt Meyer at NASA, and Ed Blanchard-Rigglesworth at University of Washington. It will also include presentation from members of the SIPN network, including Francois Maisonnet at the Catholic University of Louvain in Brussels, Johnny Day at University of Reading in England, Virginie Gumas at the Institute of Catalan Climate Sciences in Barcelona, and David Schroeder at the University of Reading in England. Julianne, at this point, I'll turn the program over to you.
Okay, great. And just a reminder for everybody, if you can mute your phone or your mics, because I hear a lot of background noise. I'm not sure if anybody else hears that, but there seems to be quite a bit.
There is quite a bit of background noise. Please, everybody, do check and make sure that that's muted, that your phone's muted. That's much better. Thank you.
Yeah,
go ahead, Julianne.
Great. Thanks, everybody. Well, so I just want to welcome everybody to our webinar. And I guess I was just going to start with sort of an overview and remind everybody kind of what our objectives are with this project. And basically, it's a huge objective, of course. We want to try to improve seasonal sea ice forecasting. And we want to do this by bringing together, you know, a group of people who are really interested in trying to improve seasonal ice forecasting. So members of a science community, so that we can get together and share ideas, run coordinated sets of experiments, share data, et cetera, that will really help to improve forecast skill. And we also, of course, want to engage with key stakeholders and others that are interested in sea ice forecasting to make sure that what we are providing in terms of, you know, metrics for different ways of expressing how we're doing with the sea ice forecasting, so that we get information to everybody that is useful to them. And I think the fact that we have more than 80 registered folks for this webinar really helps illustrate that we have a large amount of interest in this project, and I hope that it also helps indicate the willingness for everyone to want to work together to try to advance sea ice forecasting. And so what we're doing within this project is we've kind of broken things up into different action teams to sort of tackle this problem. And so we have 4 main action teams that we've identified, and these are, the first one is to coordinate and evaluate predictions, and this is really led by Cecilia Bitz. And then myself and with Walt Meyer, we're trying to look at integrating and assessing the observations that we have and what we can do to try to bring about increased forecast skill with the observations parts of it. We have Jim Overland leading an action team that's going to be focused on synthesizing predictions and observations. And then finally, we also have another action team that's really focused on disseminating the predictions and engaging the key stakeholders. And this is led by Larry Hamilton and Helen Wiggins. So while we have these sort of 4 overarching action teams that sort of help improve seasonal ice forecasting, we also have other action teams that we're developing along the way. And one example of that is we have an action team that's going to focus on the postseason report for 2014. And these folks include myself, and we have Ed Blanchard-Wigglesworth, we have Stephen Tucci, and Virginia Dumas, and Francois Massenet, and Stephen Howell. And what we'll be doing is putting together the postseason report and also trying to put together an EOS article sort of summarizing how well the predictions did this year and kind of recommendations for the future. And as we go on, I imagine we're going to have more action teams focused, but I like to put this slide up to just remind people how we're structuring it. And for anybody that's interested to get involved in one of these action teams, basically send an email to get in contact with some of the leads on these 4 main action teams. Okay, so next slide, Ed. So I just thought I'd update on kind of what we've done a little bit this year and the progress to date. I don't know if somebody needs to mute their phone because I hear a lot of background noise right now. Okay. So in 2014, we did publish a paper that we published in GRL that really looked at how well the forecast had done from 2008 to 2013. And of course, now we have this year in, and we can sort of just look at how well the predictions have done for each year. And it's interesting that when we look at it that when we see these large year-to-year differences in changes in the September sea ice extent, the predictions don't tend to fare as well as during years when the predictions are, or when the observed extent sort of falls along sort of the persistence of what we expect to see happening. But so if we look at this year, we see that we did a bit better than the year before and also the year before that. So that's good news, and I know that others later in this webinar are going to focus on how well we did this year. So I just wanted to put that up to sort of show an overview of how the predictions did this year. The other thing that we did is we hosted a workshop in April this year, and it was really successful. We had over 50 scientists attended this workshop in Boulder, Colorado. And we had a lot of recommendations come out of the workshop, and one of those was to expand the outlook to include spatial distributions of the probability of sea ice occurrence and the first ice-free date each year. And we did receive a few of these. It would be great to receive more, and ideally, I think we'd like to see us to be able to produce sort of probability maps using all of the different spatial maps that we get from different groups. But so we're trying to expand it to not just give you a metric of sea ice extent, but also the spatial patterns. There's also been a request to do outlooks, not just for the September sea ice extent, but for other months as well, and in particular July and August. We haven't done this yet. It's something that we can certainly look at doing for next year. And we do have a lot of interest in the modeling community to undertake an intercomparison study and basically investigate sort of sources of predictability, what are the observations that we are essential for us to be providing to improve the predictions and better metrics to communicate these results to different stakeholders. And I know Cece is going to expand on this a little bit later at the end of the webinar, so I'll let her expand on that. I think one thing we need to always keep in mind with these forecasts is that we really have to be careful about really articulating how accurate these forecasts can be and the limitations of these forecasts. And so I think we're trying to do that better this year with the outlook, and obviously we can keep improving towards that because I think it's very important for us to communicate the uncertainties of these forecasts. Okay, and my last slide before I turn it over is I just wanted to alert everybody that we do have a website at NSIDC, and it provides a link to various different data sets that can be used to run statistical models or ice ocean coupled models. And we have a lot of data sets out there, but it's all focused mostly on the sea ice environment and some of the ocean environment at this point. One thing we do have that might be of interest to some people is that we have 1 year of data from 10 different sea ice algorithms so that people can use these different algorithms and look at sensitivities to initial conditions, for example, in the sea ice concentration or total extent. And we've had a request also to start making available ice thickness observations that we recently reported on in a recent study in the cryosphere, which is just gridded fields of ice thickness at 2 different spatial resolutions that could be useful for some of the modelers as well. So that will be happening within the next week or so. And I guess I'm going to turn this over now to Walt, I think, to summarize how the CIS did this year.
Okay, thanks, Julian. I'm Walt Meyer at the NASA Goddard Space Flight Center. So I'll give a quick recap of how the summer went and where we ended up, and a little bit of some thoughts on why, and others may have thoughts as well in the comment section. Certainly interested in hearing any comments on that. So as you probably saw, the September average was 5.28 million square kilometers. This was the 6th lowest in the satellite record, slightly lower than last year, but obviously still well above the record low in 2012. And if we go to the next slide, this is the June contributions, and there was it kind of hit a little bit higher than the median of June's. There was a couple groups that were on target, and several that were close. Of course, at this point, I think we're in the range of still exploring and still understanding the system and looking towards improving the forecasts. And it's possible that some of this may be more due to luck than anything else. But again, at least the predictions did bracket what we ended up with, even though a little higher than the median. So looking a little bit more at the regional distribution, the figure here shows an overlay of the extent from this past year and 2013. And there is, even though the overall total extent ended up fairly same, there was some fairly substantial regional differences. Most notably, much more ice on the Atlantic side, in the Barents and Kara Sea regions, and somewhat less in the north of the Laptev Sea, particularly a kind of somewhat notable tongue of ice or tongue of open water that extended fairly far northward, upwards of 85 degrees latitude and even a little further. And then a little bit farther north in parts of the Chukchi and Beaufort as well. Going on to looking at specifically at the Canadian archipelago is another region that we don't see very well in the satellite, the passive microwave records. So Adrian Tybee contributed some information on the Canadian archipelago, and it's somewhat similar, less ice in 2013, but more than the record low in 2012. It seems to be that one of the features is there's a continued recovery of multi-year ice in the region. That's that kind of brownish color in the bar plot. Maybe a little bit hard to see, but you can see kind of an increase in the multi-year ice over the past 3 years, and that may be related to. So that's one of the things that probably contributed to greater ice this year than say 2012. But there was also a delayed start to the melt season during this past summer in the region as well. Looking at the sea ice age, these are fields from Mark Chudy at the University of Colorado. This year started with a substantial amount of second-year ice, first-year ice that survived 2013, and then aged in the second-year ice. But a lot of that did go away over the course of the winter, except for a tongue of second-year ice that extended into the East Siberian Sea, and that may have helped retain some of the ice in that area. While in the Laptev Sea, where it was all first-year ice, we were able to melt away a considerable amount of the ice cover. Another notable feature was a late melt out in the Beaufort and Chukchi Sea. That was quite different than what we'd seen in a lot of recent years. Eventually, we did lose quite a bit of ice there, but it was a relatively late start to the melt season in that region, as in the Canadian archipelago. And looking at some of the causes for the distribution and the extent that we ended up, a notable feature in terms was the circulation. We had an anomalously low pressure conditions over the Kara and Laptev seas that probably helped keep things cooler in that region, for one thing, and then corresponding to the high pressure that we typically see over the Beaufort, which was fairly normal, but essentially we had a larger than normal pressure gradient across the Arctic, which helped to engender a greater northward flow, which helped push the ice out of the Laptev region and open that area up in that tongue of open water.
Hi, well, this is Betsy. Can you wrap things up?
Yeah, it's got two more slides I'll go through quickly. In the winds, that's basically the sea level pressure pattern is reflected in the winds, and anomalously southerly winds that pushed warm air in the region and pushed the ice northward, along with the northerly winds corresponding to the low that brought cold air and pushed the ice southward in the higher ice region of the Barents and Kara seas. And then the final slide, looking at the air temperatures, again, you see this reflected with a colder than normal summer over the Barents and Kara seas, a little bit over the Beaufort Sea region, but warmer than normal in the Laptev area. This is a bit of contrast to 2013, even though the extents were, the total extents were roughly the same. 2013 was more of an average year throughout the Arctic. And then 2012, which I don't show here, was a very warm year throughout the Arctic, as we had talked about in the past. So, thank you.
Okay, thanks. So I'm giving here a quick overview of the subset of modeling contributions for the 2014 outlook. And before I show the results themselves, I think we should have a look at a table that should appear on the screen. Oh, yeah. Thanks. So the table is quite comprehensive, and I don't expect you to read it in full details. But each column represents a contribution from a modeling group. There were 10 of them for August, and I used several colors to identify similarities and differences between the groups. Next slide, please. Oh, yeah. Okay. So just show the table like this. Yeah. Not the table. Okay. So if you now look at the top row, you can see that there are two main classes of contributions. You have those contributions that were conducted with fully coupled models that I show in yellow in the top row, and you have the contributions from forced contributions. So in this case, the atmosphere is fully prescribed. And it's very important to make this distinction because there is a reason that is important I will explain soon. You can also see that the models differ in the domain they cover. You have global and regional models. But to me, I think it's important for the scientific question, given the very short time scale that are involved in seasonal prediction. Now, if you look at the second big frame, you can see that seasonal prediction is an initial cognition problem. So each group had to somehow initialize their simulations to expect some skill. And the colors are very qualitative. Green means that the components, so the atmosphere, the ocean, or the sea ice, was initialized. Orange means that there was some indirect initialization, and red means that no initialization was applied. And the good news from that frame is that the green and the orange colors prevail, and that the ice itself is most of the time initialized. Now, if you look at the third frame, the evaluation of uncertainty, it's also a very important frame because each group is supposed to provide, in addition to a prediction, a range reflecting the uncertainty in the forecast. The good news is that most of the groups use a large number of numbers to estimate this uncertainty. but I have the feeling that only a part of the sources of uncertainty have been explored. What I mean is that most groups investigate the uncertainty associated to the unpredictable atmospheric forcing. Only 2 groups run simulations that start from different initial conditions, and none of the groups has explored the uncertainty associated to the model imperfect physics or to some model parameters. So I have a good reason to believe here that the estimate of uncertainty that is provided by each group is probably conservative in the sense that it does not account for the cumulative effect of the unpredictable atmosphere, the imperfect initial conditions, and model physics. The diagnostics frame, I'll be very quick on this one. Of course, all groups are supposed to provide KS extent as a diagnostic because it's mandatory if you want to participate in the 2014 outlook. But it's very encouraging to see that other metrics start to be used besides KS extent, and these metrics, including the I3 date, are probably more relevant for end users. Okay, you can turn to the next slide. The one with yes, this one. So these are the results for the 2014 outlook from models. There are really 2 main features that I want to point out here. The first one is that if you look at each prediction individually, so if you take, for example, the Coker prediction, then the overall, the second one, then the third one, the fourth one, then you can observe that the range of each individual prediction gets in general narrower and narrower as we move from the June outlook to the August outlook. And this is just saying that more confident predictions can be issued for shorter lead times, simply because the unpredictable perturbations in the atmosphere have less time to develop. But the second main feature, I think, is much more interesting. If you now consider all contributions as a group, then, for example, looking at the median, then you will notice that collectively the predictions become more and more correct and confident over time. Now we know that all these models run at different resolutions with different atmosphere models, ocean sea ice models. We know that the parameters are different, so we can really say that the structural uncertainty related to parameterizations, model physics, etc., is also reduced as we approach the prediction date. Now you can.
Betsy, can you move
yeah,
things?
This is my,
can you conclude
I'm working at slide, finishing slide. So yeah, really to finish, I think that the first message is very encouraging and it's saying that the models do have skill and even better skill as the time goes by. The second message that I want you to take home is that unfortunately I think that the width of the confidence intervals around the predictions is probably too low because some sources of uncertainty have not been explored. Yeah, thanks.
And I think that means that I'm live, so I hope you can all hear me. And I'm just going to discuss a couple slides with the results from the regional aspect of the outlook, and specifically the spatial probability of ice extent and the I3 dates. And here I show you 4 different submissions of sea ice probability. And these are all from groups that submitted to the 2014 Outlook, so thanks to them for submitting these fields. And what you see here is the probability of sea ice extent, that is sea ice concentration greater than 15% at every grid cell in the native grids of its model. And you can see there's a fair bit of range among the 4 submissions, but 3 of them, the bottom row and my own submission in the top left, they do show sort of some characteristics like, you know, greater sea ice in the East Siberian Sea and less sea ice in the lap turf that were in observations. And Richard Clutter's NASA in the top right, that's a more perhaps homogeneous sea ice edge, but they, I think that total sea ice extent was not too bad, maybe on the low side. Now, what I have done with these 4 submissions is I've created a multi-model ensemble mean. So this has taken the 4 previous fields and create an ensemble mean there. And so what you get is what you see on the left. And I am comparing with the observed September sea ice extent. So a perfect forecast would look like the field on the right, but we don't think we could ever expect to get that. It's still a research issue how to assign a number, basically, to the field on the left and how well it represents the field on the right. And perhaps, you know, you can imagine taking the 50% outline and then the spread about that 50% line. But at least from visual inspection, it looks like the multi-model ensemble mean does fairly well. It gets the little sea ice in the Laptev, East Siberian ice tongue. Sorry?
We've got somebody that needs to mute their phone. And Ed, if you can wrap things up, that'd be great.
Okay. So that's encouraging. And then the other field I wanted to show were the ice-free dates. And these are the dates of melt. With bottom left in observations, and you've got a cheat sheet at the very bottom left of what the numbers are in terms of first day of the month. And again, there's a fair bit of range across these fields. But you perhaps, you know, kind of generalistically and maybe being generous, we get some of the features like that kind of parallel the sea ice extent probability maps. And I would love to encourage other groups to submit these sort of fields. And with that, I will pass on to the next speaker and ask to be muted.
Okay, I hope you can hear me. So, yeah, as Ed and Francois have been describing, there's been a lot of work towards developing dynamical seasonal forecasting systems for forecasting sea ice. And essentially these models, a lot of them take in observations through a process called assimilation or initialization to create a best guess of the current atmosphere and ocean state. But very few of these systems are currently using sea ice thickness observations to start their forecast. And essentially what I'm presenting here is an idealized experiment. I should stress that it's not a forecasting system, but it is to determine how much skill can be gained from accurate sea ice thickness initialization. So essentially what I've done is 2 sets of forecasts. And they're identical, apart from the fact that one of the sets of forecasts was initialized with climatological sea ice thickness, and the other was initialized with essentially perfect knowledge of the sea ice thickness field. So because it's in a model, I'm sort of going to refer to it as sort of pseudo observations. So and essentially what's shown here is normalized root mean square error for these different forecast sets. So if you look at the dashed lines, which refer to the this set that sort of started in July. So the black line shows the set which are called SIP in it, which are the ones that were initialized with the thickness information, and the red dashed line shows the one that wasn't. So it was initialized with sea ice thickness climatology, and you can see that if you look at to September, which is the third dot along the line, you can see that essentially the forecast skill is essentially doubled, i.e. the error in the forecast is halved by having accurate information of the sea ice thickness field, which is interesting. And more to the point, it's very different to the forecasts that are initialized in January. So if you look at the 2 solid lines, they're almost identical, certainly for the first 6 months. So moving on to the spatial maps. Thanks. So So these plots show the difference in the scale spatially. So these are, so where there are large differences, there's essentially a large improvement in the set of forecasts that have CI thickness information in them. So if you look at the top row, you can see that the difference in these two different sets of forecasts decreases over time. So when they start off in July, there's quite a large error, which is what I've kind of been imposed by the experimental design. And then these decrease over time through September and have almost disappeared by the following March, as the memory of the initial state decreases with time. So, but if you look at the bottom row, you can see that the CI's concentration field is also very different. So in July, there are large differences in the size of the forecast errors, particularly in the marginalized zone, and these are still there in September. But obviously, they've shifted to the September marginalized CI zone. And this is why we have such large differences between these two experiments in their forecasts of CI extent. And essentially what's happening here is that as the sea ice edge sort of wanes with the melt season, the reduction in ice extent depends critically on the sea ice thickness. So essentially erroneous ice thickness in the SIPN set, which was initialized with the sea ice climatology, essentially leads to large impacts in melt and therefore in concentration. And so we can conclude from this that if we think that the model does a reasonable job of representing reality, then we can conclude that sea ice thickness information is going to be fairly crucial for producing accurate forecasts of summer sea ice cover. Okay, thanks.
So hi. Thanks a lot for this opportunity to present the recent progresses by the Climate Forecasting Unit led by Paco Douglas Reyes. We are a few members focusing on the Arctic sea ice predictability and prediction. So I'm working with Neven Fushkar, who is a research scientist, Daniela Volpi, who is finishing her PhD by the end of the year, and two engineers, Asif and Uriel. Neven Fushkar has already presented in the Sea Ice Prediction Network workshop in spring our work on generating sea ice reconstructions, which are as close as possible from observation and which allows to initialize our dynamical predictions. So I won't give more details about this reconstruction, but I'm showing here his recent results on the extraction of the Arctic sea ice modes of variability. A classical way of extracting modes of variability is based on the empirical orthogonal function, but these assume a number of statistical hypotheses which are not which are not fulfilled by the sea ice variables, like sea ice concentration or sea ice thickness, which are bounded. So a much more suitable way of extracting sea ice modes of variability is based on classification methods. Imagine that you have 50 years of data, that means 50 years of winter mean fields. The idea is to group these 50 patterns into a limited number of classes with as small as possible a variance in a class and as large as possible a variance between the classes. So this methodology has allowed to obtain 3 robust modes of Arctic sea ice variability based on the sea ice thickness, which are illustrated on this slide, with the little black dots illustrating the region where the variability is significant. And you have the percentage of occurrence over the historical period of each of these modes indicated in the bottom left corner. And the bottom left figure in the panels of the slide illustrates when each of these modes has occurred over the period 1979 present. So this panel illustrates the interannual to decadal variability of these modes. So these are the modes extracted from the winter patterns, but similar modes are obtained from the summer patterns. And this is being prepared for publications. And these patterns of variability, this mode of variability, in the future will be, we will investigate, we are currently investigating the mechanism that leads to the occurrence of these modes. we'll build statistical models that allow us to predict these modes and develop scores based on hit rate and false alarm rate in dynamical prediction. Another result I wanted to highlight is the work by Daniela Volpi. So a classical way of initializing dynamical prediction is to use raw observation. This methodology is well known as full-field initialization, and there is an alternative way which is being developed called anomaly initialization that consists in, instead of using raw observations, adding observed anomalies on top of a model climatology. This methodology allows to avoid the initial drift, since with full-field initializations, the dynamical predictions drift toward the model climate, and afterward, even with bias correction, it is difficult to disentangle the climate signal to predict from the climate drift. So she has furthered the idea by using a weighted CIS anomaly initialization, and the idea is to weight the observed CIS anomaly according to the different variance between the observations and the model before adding to this anomaly to the model climatology. And the results are illustrated on this figure on the root mean square error of the ensemble mean Panarctic CIS extent on the left and Panarctic CIS volume on the right as a function of the forecast time. This uncast lasts 5 years, so the x-axis consists of 5 years. You can see on this figure the classical full-field initialization illustrated in red. The historical simulations in which there is no effort to initialize from observation is illustrated in orange, and you can see that initializing from observations allows to reduce the error in the forecast. Using classical anomaly initializations in the ocean and the CIS components, in purple, you can see that we have further reduction in the root mean square error. And using this improved anomaly initialization method where the observed anomaly are weighted in green, we obtain even further improvement in the forecast skill. So thanks a lot for your attention.
David, this is Betsy. Are you able to join us? Are you able to move forward? Well, then, Ed, why don't we move forward to the next discussion, and we can come back to David when he is able to join us. Does that sound good?
Right.
Celia,
yes, can you hear me?
Yes, that'd be great. Thank you.
Great. I'm happy to fill in, but David, let us know maybe by chat if you can make your system work. I can see you turning on and off your microphone, but we still can't hear you. So thanks to everyone. This has been really exciting to hear great things that have happened within the CIS Outlook, and also the research highlights really illustrate how this is a joint effort of producing those outlooks, and also specific research that informs us about predictability as well. So I guess our next step that we really want to pursue is a more organized and specific experiment to explore how initial condition uncertainty influences our predictions. And this will be open to anyone who's modeling and statistical as well as dynamical models. We will definitely have some challenges creating the procedures that everyone can use with their different methods, and so it's going to take some effort. What I'm expecting to do is to create a kind of plan that would be then discussed in more detail at the AGU, and we hope to gather as many people together as can come in a real hands-on action team. That would be for modeling, but I'm sure there will be other groups that want to talk about other aspects of CIS outlooks and the CIS prediction network. So it's not just exclusive, but that's at least one concrete thing we want to do. And then in future, after we come up with a plan, I think we'll probably want to have pretty regular teleconferences of all of the participants who are able to be involved in that activity. So basically, I'm proposing that we're going to really increase our contact time together in the future, but we'll start with AGU. The other thing I want to do is just put in a picture. Ed already did, but we're super grateful for all of the people who contributed these expanded diagnostics this year. And I think that really gave us some new details and things to talk about that have advanced our understanding of what's possible and where we should go. So thanks for all of that. And at this point, I'm going to end. And can we get David back on? And if not, we'll move into a group discussion.
Can you hear me now?
Yes, I can. So why don't you just take over?
Okay, great. Yeah, sorry about the problems. Our forecast is based on melt points. When snow and ice melts in spring, not all the meltwater does run immediately into the ocean, but some of the meltwater forms ponds. And over the last 10 years, we have developed a melt pond model that is able to simulate the evolution of melt ponds. The main principle of this model is that it is based on the topography of sea ice, so that the meltwater runs to the lowest sea ice, to the thinnest sea ice first. Which seems to be valid for the small scale, but it also works in a climate model where we only have, let's say, 5 ice thickness categories. Can I go to the next slide, please? Here you can see the results from a standalone size simulation where we implemented the melt pond model. And if you first look at the black line, you see the average total melt pond fraction of sea ice in the Arctic, starting in May. So the first melt ponds occur in May, and the maximum is in mid-July. But the main thing is you see also huge variability between the different years. So if you look first at the decades, the blue line is for the early decades from 79 to 89. You can see that the amount of melt ponds was much lower. And in the last 12 years, the amount of melt ponds was much higher. And even in some extreme years, 2012, the year with the minimum ice extent, has the maximum amount of melt ponds, and the year 1996 with a maximum ice extent, a very low amount of melt ponds. I want to say this is just a model product, and which gave us to check how well it is correlated with the September ice extent. So, and we did check that first with the September sea ice extent in our model simulation, but it is also very highly correlated with the observed SSMI sea ice extent. And we have a correlation coefficient of about 0.8 for detrended time series of the total pond fraction and the September ice extent. Next slide, please. So if we actually use then this simple linear correlation between the total pond fraction over the whole Arctic and averaged over a certain time period, let's say here for May and June till the 25th of June, and use this correlation to forecast the sea ice extent. So you can compare the black line, that is the observation, and what we call here the hindcast is the red line. So we see that actually there's quite a good, only small differences between the observation and the so-called hindcast experiment. But of course, for a real forecast, we don't have the information of the future years and this year, so we can only use information from past years. So the skill drops a bit. But nevertheless, if you look at the blue line, we do capture quite a lot of the interannual variability. So our, if you look at on the right side, our forecast error based on the last 25 years is about 0.44 million square kilometers. And if we calculate a skill, this is normally a skill can either be 1 if it's a skill is 1 if it's a perfect forecast, and 0 if the forecast is not better than any other simple forecast for comparison. We choose for comparison. This is normally if you just forecast, it follows the trend, and we have a skill value of 0.41, and this is comparison to other quite a high value. But the interesting thing is actually why do we get such good correlation between the point fraction and the September ice extent. And of course, there are 2 reasons actually. First, there is the obvious one, there is the strong feedback. So if meltwater forms, it reduces the albedo, so we have a strong increase of melt, so we get more meltwater and even a lower albedo and more melting. So if the melt point starts early enough, when there is time enough to melt the ice completely. But of course, if that would be the only reason, we could also use just the amount of meltwater available at the beginning of the season. A second point, what is quite important, is the preconditioning that is captured. Because we have in our simulation, there's quite a big difference between first-year and multi-year ice. On first-year ice, the same amount of meltwater does spread over a larger area, so it has a much stronger impact, whereas on multi-year ice, the same amount of meltwater runs in deeper gaps, and so only a small area is covered, and so the impact is much smaller. Thank you.
Okay, this is Betsy. Thank you all for fabulous presentations. At this time, we have about 15 minutes for community discussion. And I want to remind you that to participate, you can ask a question by either raising your hand in the participant panel or entering text in the chat panel. And I don't see any questions right now. Cecilia, would you like to continue the discussion?
I can try. I think what happened when we started the discussion was all of the presenters went off mute, so we had a bit of feedback. It looks like it's good now. Up and down. So maybe I can describe kind of what our vague early plan is for a bigger, a more organized intercomparison. And coordinate groups so that they get as close as possible to the same initial conditions, and that way we can eliminate that as a source of uncertainty among the different methods for our Sea Ice Outlook participants. But then there's going to be another factor, and that is that there are many, many different ways people produce their initial conditions. Some people just prescribe observed, and others incorporate that into some data assimilation procedures, so they get connections across other variables in their model. So we'll have different types of methods for these different, or we'll have different procedures for these different types of methods.
Hi, Cece. This is Betsy. It looks like we have a question from Ram Rajak. Ram, would you like to unmute and ask your question?
This is Ram Rajak. I wanted to know what was the length of time series which was used for Sea Ice probability calculation.
Ram, I'm not sure that I understood your question. Could you repeat it more, a little bit more slowly? Cecilia, did you understand the question?
Yeah, I did not understand the question.
Okay, Ram?
the CI probability was calculated. That was how long data was used for calculation of the CI probability? I wanted to know that.
I think I understand that you're asking how long did we make these predictions? So when were they initialized? And it varied as a function of the season. So the very first predictions were made on June 1st. Well, I should say that they were submitted very shortly after June. So many people were finishing off their activity right around June 1st. And then, getting even more advice about what the question was. What was the time period used to compute the probability of ice? In Ed's calculation. So I think we did it twice for July and August. So the last time was in August. So the lead time, the forecast lead time would have been a month. And I think that's what Ed showed. Is that right, Ed?
You hear me?
Thank you.
No, so the probability of CIs is actually calculated using the ensemble for each submission. So each model, if we have 10 members for each model, then if all 10 members have CIs at a grid cell, we assign that a CI's probability of 100%. And if only 5 of them had, that's 50%. And if none of them had CIs in that grid cell, then it's 0%. So for these calculations, it's crucial to have a to have an ensemble of outlooks, because if you just have one run, then we can't assess that probability. And I will comment that as and let me go back very quickly to that slide here from Francois. If you look at the number of members in the evolution of uncertainty, then it's great that every group has, at least 7, and most people have 10 or even more members. So we can build pretty good ensembles out of these.
This is Betsy again. I don't see any other questions with hands raised. I think that there were a few people who intended to make comments afterwards. This would be a good time for you to jump in. And again, if you could raise your hand, I can call on you. Or if you type a question in the chat box, we can read your question there. Is there anybody else that would like to join the conversation? Okay, seeing none. Cecilia, Julianne, or Ed, or is there any other comments people wanted to make that were the presenters, follow-up comments to their presentation? Julianne, did you have anything else to add?
I'll just ask, we are also always very interested in getting your feedback on how we could make this process better. And if you are too shy to say it over the webinar, emails are a perfectly good way to talk to us as well. Pick up the phone. We're happy to talk, and we consider everyone who's connected and receiving our emails as part of our network.
And again, to join the network, you can go to the SIPN website, arcus/SIPN, and there is a form to complete to fill out and join the SIPN network that way and get information and emails. Also a great way to start conversations, and we can forward them and include them to the rest of the network.
Hi, this is Julian. Can you guys hear me?
Yes.
Okay. I noticed that Drew Slater had posted a comment. And I don't know how many people, I think only Drew Slater might be the only one using a statistical forecasting method that did also give a map of where the ice is going to be. And I definitely would encourage people that are also doing statistical forecasts to submit maps, probability maps as well of the sea ice. I think it'd be really useful to be able to compare that more with not just the statistical methods, but also with the modeling methods as well.
And this is Betsy. I do not see the comment from Drew. Would you care to read that comment, Julia?
Sure. It said, unfortunately, you missed someone's map. That one looked quite good. So I think Drew was referring to his forecast. So I know when he does it, like a few weeks out, he actually gets pretty good predictability with that. And I think that that's what he's referring to.
Great. Thank you.
Although if Drew's on the line, he can comment himself.
Drew, are you online? Okay, we've got about another 5 minutes of the webinar remaining. It really is a good time for people to chime in with questions or comments if they have them. Again, you can raise your hand in the participant panel or write a comment in the chat panel.
So this is Cecilia. I'm interested if any, since maybe it's just panelists that are able to talk at this moment. I'm not sure, but that may be one of the reasons we're not getting a lot of comments. Would any of the panelists care to comment on their interpretation of why the sea ice observations were the way they were this year? Do any people have a perspective that might be different from the one Walt presented about why ice is, at least among our predictions, on the high side?
I guess I'll make a comment. I think what this year shows is that, and even last year, that if we don't have any sort of anomalous atmospheric forcing, like we've had, for example, maybe in 2007 or even in the years following that until the last 2 summers, that the extent sort of ends up where we would expect it to, and it pretty much falls not too far from the long-term linear trend line. And so I think that perhaps what these last 2 summers indicate is that if you don't have strong anomalous forcing from the atmosphere, that you might just expect the sea ice to continue along this long-term trend line. I mean, that's one thought that I have. Others might have a different thought, but that's sort of what it looks like to me. If I plot the departures from the trend line, that's what it looks like right now.
Are there any other comments from the panelists?
I would, I don't know if you can hear me,
Yes, we can.
but I would second that. And just looking at even the regional features of the sea ice edge, especially this combination of the Laptev melt back and the East Siberian sea ice tongue, for want of a better name. That seems to have been both a combination of the kind of initial conditions in the spring, what Walt was talking about, the sea ice age, and it's interesting that a few of the modeling submissions that I showed kind of capture that, but it seems to have been accentuated by the summer circulation patterns, so those southerly winds in the Laptev and the northerly winds in the Kara kind of enhancing or contributing to that regional feature. Yeah, no, I think what Julianne was kind of alluding to, it's, you can also see that perhaps in some of the regional features.
Hey, this is Tayo calling in. Sorry, I missed the first part of the conversation. I just got back from teaching. But one point that I thought was very interesting this summer both from the perspective of looking at how sea ice evolves over in the Pacific sector, where we've seen quite a bit of reconstitution of multi-year ice, but also from the perspective of how the outlook helps us gather near real-time observations of the state of the ice cover. And specifically, I'm referring to the ONR's marginal ice zone experiment that had a really nice set of buoys spread out over the Pacific Arctic sector, where a lot of the offline discussions that we had with people who were both tracking the forecasts and looking at what validation data come in, noticed that the state of the ice cover as shown by the buoys deviated quite a bit from what we would have expected based on other evidence. So I thought that was an interesting lesson as to how you can validate, and it actually resulted in interesting validation in the near real time by lining up specific observations for parts of the Arctic with the comprehensive observations that are available for that region. So if people have ideas on how to foster more of this near real-time discussion, evaluation of observational data, and providing background information on how the ice cover evolves in different sectors, that would definitely be something that we would be interested in getting feedback on, either in writing or in some other form.
It's 1 o'clock.
Hi, this is Betsy, and it is 1 o'clock. I think this has been terrific discussion. We really appreciate everybody that has participated, and especially the fabulous presentations from all 8 panelists. The discussion can continue via the SIPN email, as Celia suggested, and please remember that there will be a meeting planned at AGU in December, and that all of the SIPN leadership team is anxious to hear from the network and keep the network moving forward in a successful manner. It is 11 o'clock, or it is past the hour, and probably time for us to shut down. If there's any last comments from Cecilia or Julianne, this would be a good time, and otherwise, I'll give one more chance here. Any last comments from the team?
I'll just add my thanks. That it was really nice to have some of our colleagues from international participants in the Outlook contribute to this activity today. With not just our leadership team, but at least half the presenters were visitors or guests. So thank you very much.
Thank you.
Yeah.
Thank you all for participating. Oh, go ahead, Julianne.
No, and I guess I would like to mention, too, that a lot of our European colleagues are going to be involved in writing the post-season report, and as well as the EOS paper. So I think it's really great to be working together on this.
That's right. A good thing to mention is that the Sea Ice Prediction Network has a series of post-season activities. This webinar is the first. 2 other activities that are planned and will be kicked off by a newly formed action team are the post-season report, and then also an article for EOS, as Julianne mentioned. Again, please feel free to send your comments or suggestions via email to any of the leadership team, or submit them through the SIPN membership form, which you can submit online. At this point, we'll conclude the webinar for today, and again, thank you all very much for your participation. Goodbye.